What happened? Huh? Should I share it again? Okay. Media. Live. Will you start? Okay. Okay. Good morning, everybody. Let's start the session then. So it's okay in Zoom as well. Okay. So today what we will do is we'll go ahead and then look at some of matrices stuff and linear transformation and decompositions. So that's the plan for the whole morning together with the tutorials. Okay. Fine. So yesterday we were discussing, we also have to know some little bit programming to take the full advantage of SageMath. So I try to actually do little bit of programming as well along with the course. Okay, meaning along with the content that we are doing. Okay, maybe as a revision and just for short refreshment, let's define two vectors. Vector, I'll define it in rational field. Say 1, 2, or 1, -1, 2. Then V2 is a vector, and then 2, 3, -1. Okay. Hopefully that's fine. Now I can try plotting this V1 as it is, and that should give me the plot. And it's a three-dimensional vector, as you can see. This is the plot. Okay. Of course, SageMath is a little bit clever enough to actually give us the view in both directions. So we can look at that angles as well. Now, if you want to plot the other one as well, then you have to at least just add that plot along with this plot. If I am not wrong. Yes. Yes. This is how you plot the vectors. I think it would be better if you have a two-dimensional vector and then see it. We remove the last entry and then rerun that. And now I think it is clear for you. Okay. There is also another function called arrow that you can use it to plot vectors as well. This one simply actually takes that tail of the vector as 0, 0. It's not all the time that the tail of the vector has to be 0, 0. Tail of the vector can be anywhere in the vector space. So at that time, what you have to do, you have to use the function called arrow to plot this vectors. Okay. Yeah. I'm not going into that because it takes more time into this. I'm not doing that. Anyway, you can do it by yourself. So I'm going to retain those numbers, what I had earlier. So these are the numbers I have, okay, for your information. One minus one, two, two, three, minus one. So if you're okay. Origin is 0, 0. 0, 0, 0. Because the graph is like this. So if I do 2 times V1 plus 3 times V2, that's the linear combination we have looked at, and we know that those things are actually easily available. Okay. And I can do a dot product. Nothing new, whatever we have done in the previous class only, previous session. So V1 dot product with D2, just obtained by writing V1 dot underscore product of V2. And it's a 3-dimensional vector, so we can also look at the cross product of it. So that's not a problem. That becomes a vector. Okay. Let's take a vector 3, 2, 5, and then another vector 1, 2, or 1 minus 2, 1. Now we'll calculate a P as follows. V dot product of U, then divided by the norm of U square actually. Norm of U square, and then multiply by U. What did I do now? Actually, I just generated one new vector like this, and that vector is the dot product of U and V, and then times U. Where will this be? Maybe we'll try plotting this P. Check where is this? This is here. And then probably we'll try plotting the U as well along with that. So U and P is now in the same directions. That is clear, right? Obviously, it has to be because the dot product is some scalar which we have multiplied, and then we just divided by another scalar, and then we multiplied that with U. So P is nothing but is a vector which is in this which is in the same direction. What about the V? That's my V over there. So now let me try plotting U, and then P minus V, or V, whatever, V minus. It's not really clear right away, but can you see that these two are orthogonal to each other? I do not know what is the perfect angle to keep it. Yeah. Yeah. So U and V minus P are orthogonal to each other. We can verify it. How do you verify it? Just do a dot product of U with V minus P, and that should be 0. That means U and V minus P are orthogonal to each other. Okay. Fine. So now what we can do now, we can actually find orthogonal projection of V onto U. Can someone tell me how do you do so? We've already done that. Okay, my intention is to actually introduce you to a function. So given two vectors, V and U, now that function should return an orthogonal projection of the first vector onto the second vector. That's the idea. So what I want to return, let me make a comment here. What I want to return is return the orthogonal projection of V onto U. Now this is simple linear algebra. It says you try finding the meaning actually return this vector that is becomes a orthogonal projection, right? What is that? You would have to do a dot product of V onto U, and then you actually multiply that with the U. That's going to be orthogonal projection. I think usually we also will divide it by the norm. Okay. So that gives an orthogonal projection. So now let me actually save that as a P projection of I already have the V and U. If you remember what I had here. Where is my U and V? Here is my U and V. Maybe I'll copy this and then paste it here. Now I want a projection of V on U. I print P, then I get the P. This is exactly what we have calculated just now. The only thing that I have done right now here is we put it as a function now. That's all only thing. So this is the way you define a function in Python in general, and evidently in SageMath. So whatever you want to do with some inputs, take them as an input first of all, and then return the computation whatever you feel like doing it. Yeah. So over here, what we have done a dot product of U and V, and then multiply that with the U. So therefore, that gives me a orthogonal projection of U and V, V on U. Obviously, if I do the other way around, you know what will happen, right? So for example, if I do a U comma V, then that will be a projection of U onto V. So it's basically a projection of the first vector onto the second vector. Okay. So now let's look at how to solve system of equations. There are many ways of solving system of linear equations, but I should say linear equations actually. we'll take up whichever actually gives us some learning perspectives. First of all, you have a system of linear equations means, first of all, what you have a variables in hand. So how do I actually define a symbolic variable in Sage Math? Is just simply just to whatever the value you wanted as to be called as a variable name, and then give the symbol that you wanted. For example, I can do like this. So now if I do X, then that X is actually been considered as a symbol now. You can even write the type of X, and that says that it's a symbolic expression class. And it's an instance of a symbolic expression. That means now what I can do, I can now multiply that X. I can now add a number to that X. So all my calculation now, this is not going to be an error. Yeah. If I, let's say, suppose I give simply Y, and remember actually I had a X here, I ran the cell, but it was not throwing any error. But if I just simply say Y and then ran this, obviously it gives me a name error because I do not know who is that Y is. So if I wanted that Y also to be considered as a symbolic variable, then what I should do? Yeah, I'll leave the error as it is. What I should do now? I should say Y equal to variable of something. Okay. Whatever you want. It's not like it has to be only Y only. Now, if you say Y, then you can see that Y is nothing but a symbolic expression for the another expression called something. So I can literally have anything I want, like so for my name, actually I can do that. So that means I can do twice of David, thrice of David, square the David, everything is possible. Because I made it symbolic. So if you have 2 or 3 variables together, and what you can do is you can club them together like this, and X, Y, Z, and that will generate the 3 variables at a single line. Simple way of working on it. Yeah. So let's do one thing. We'll generate one equation on all these 3 expression. So the equation in Sage Math is written like this. You take any expression in terms of X, Y, Z, because we have the X, Y, Z as a symbolic variable now. So now I'm just picking up one equation here. And now you see, okay, plus Z. Now it's an equation. So in Sage Math, what we should do is we should write double equal here. Have you hopefully you're noticing this? So this equality is going to do an assignment and of what? Of this expression over here. So this expression also has one equal to here, but this is a double equal instead of single equal. And that says that actually this is itself together as an expression where the left hand side is equal to the right hand side. Yeah. Now, if you print this equation 1, and then you know what does it mean, by the way. Yeah. Similarly, let's type the equation 2. 2 times Y plus 3 times Z equal to minus 3. And equation 3 is 9 times X. Remember, I'm not writing 9Y as it is. Yeah, that has no meaning here. Even if you compile it, it will tell it's a syntax error. Obviously, I made one more syntax error here. I should do a star in between. Yeah. So I cannot simply write 3Z or 9Y, etc. I have to do, I have to tell it to multiply. Literally, that's what it is. Then plus 3 times Y, 9X. Thank you for the correction. 9X plus 3Y plus Z equal to 2. Actually, equal to 2. Yeah. Now that's okay. So I have my three equations and how will I solve them? Now Sage Math automatically has by default has a function called solve. It takes two argument, call it as AB. Now the first argument is a set of equations given in an array. Now I know who are they. Now equation 1 is the first equation, equation 2 is the second equation, equation 3 is a third equation. So the option A is simply that. And what's the second equation? Second option. The second option is these equations are on what variables? So these equations are of what variables? That also has to be supplied as an array. So x comma y comma z. Okay. So now this will solve the equation and gives the solution. So over here you can see the solutions are x equal to 101 divided by 79. That means the value of x is actually 101 by 7. Yeah. There's one more way of solving this as well. What you can do is you can construct a coefficient matrix from the equations. Now, I know that the coefficient matrix from this equations would be, can you tell me what is that? Yeah, 1 minus 2, 1. And then the second row would be 0, comma 2, comma 3. And the third one is 9, comma 3, comma 1. So that's my A, the coefficient matrix. And B will be simply a vector, and that vector has the values 10, comma minus 3, comma 2. Okay. Now you see what I have tried to do here is I have tried to formulate the expression AX equal to B. And then I was trying to solve this problem. That's all. And that X is actually now a variable X, Y, Z. That's the idea. Now, how will I solve this problem? Using this, maybe I think it's a I'll say, I don't know. I should not call method though. It's exactly same, I guess. I'll call it as weight. Another way of doing it. The way I solve this is A dot solve underscore right, and on this braces you should give what will be the right answer, and that gives the same answer if you notice already. So A dot solve right. There's also A dot solve left, and what that will do is that will solve this equation. What is this equation? X into A is equal to B. It will solve this equation. If you solve left, so obviously that's a different solution. So this is the one we needed, because usually what we do is we solve this expression only, AX equal to B. Is it okay? Everybody is comfortable now? Yeah. There is also one more MATLAB like way of solving it. It's just give A, then the backslash, and then B. In MATLAB we do it. So there are 3 ways of doing the same. There is one more way of doing it using RREF or REF. I believe you know what is RREF, right? What is the RREF? Row reduced echelon form of a given matrix A, correct? And REF is the row echelon form of given matrix A. So given any matrix A, you can actually call this function called REF. Why is not working? I think it's supposed to be row echelon form. Not echelon form, it is. Yes. So given any matrix, you can call this function called echelon form that gives you a row echelon form. That's all. Similarly, you can also call the RREF function like that, and that will give you a row reduced echelon form. Yeah. So if you have already learned Gauss-Jordan and Gauss elimination and Gauss-Jordan elimination methods, now the Gauss elimination method uses row echelon form, and Gauss-Jordan elimination uses row reduced echelon form. Correct. So the difference between them is just simply we call this as pivotal elements. So this one, and then this 79, all of them are actually pivotal elements. Above and below the pivotal elements, if you have made all the other entries to be 0 by using row operations, then we call that resultant as a row reduced echelon form. And the otherwise, actually, it is row echelon form. Just leave the entries which is just below the pivotal entries 0. Don't bother about the people who are above the pivotal entry, and that becomes a row echelon form, correct? So now how do I solve using row reduced echelon form? The first thing that I have to do is, how do you have to solve this problem? It's not just you solve AX equal to B right away, but what you have to do is you have to formulate something called as the A augment B. And then what do you have to do? You have to find the A augment B. Then what you should do, you should find the row reduced echelon form of it. And that will give you the last column, simply the solution, correct? Yes? Comfortable, right? Should I write it? I think. Hopefully that's fine. Yeah. So I just have to look at the corresponding row reduced echelon form of RREB. Okay. I don't know how does this annotation came. Yes. Clear all drawing. Yes. So for that, first of all, I should augment B with the A. So let's do that. Now let's call it as maybe AUG, A augmented is actually equal to A dot. Now SageMath actually have a function called augment B. Now if I do A augment, and now you can see that the B column, which is 10 minus 3, 2, is actually augmented. Yeah. If you want to clearly see it, you can actually turn on the subdivide equal to true. And that will give you a small bar. Probably show of ARPG will give you a better way of looking at it. Yes. On any matrix, actually, you can call this. In fact, any expression you can call it as show, because it's a special function defined in SageMath. which gives you a better, which is having a later compatibility that makes it a little bit easier to see. That's it. Yeah. So now you can see this is how actually we look at the augmented matrix. Now what we can do, we can look at the RREF of the augmented matrix. Now you know who is this fellow, right? Maybe I'll call a show method on that as well. Now can you see the last column? The last column is simply the solution of the expression over there, correct? Now how will I fetch the last column? So for that, what will I do is I'll first actually save it as A underscore RREF. I'm trying to make it so meaningful. So this is the exact same thing. But what I need only the fourth column of this matrix, because the fourth column of the matrix is the only solution over here, right? So how do I actually get it? Now in Python, in general, the index starts from 0. Therefore, the first column is typically called as 0th column, and 1, 2, and 3. So originally, whatever the fourth column right now is actually in Python sense, it's a third column, correct? So I have multiple ways of actually fetching them, but Python has an easy way of doing it. Is if you look at that matrix and then call a column method on it, and then if you write column and then the index of the column in which what you wanted, and that gives you the corresponding value. So now it's clear that this is the solution. Okay. Let me repeat what we have done right now here is Python has a zero index policy. That means it doesn't start counting from 1 to 3, whereas it starts counting from 0, 1 to 3. So whatever typically we call it as 1 is actually been called as 0, and so on. So the fourth column, whatever we needed, was in the Python sense, it's actually the third column, because 0, 1, 2, and then 3. Okay. Yeah. So let's practice the programming little bit more. Maybe what I will do, actually, I'll give you a minute to formulate this as a function. So what it should do, it should take a matrix A, and then it should take a column vector B. It should result the solution using the RREF. How do you do it? So my question is simple. Prepare a function to create or to solve system using RREF. That's my question. Yeah, it's too much, I guess. So how do I do that? Define the function name. The function name is, maybe I'll do very explicit function name, solve using RREF. Now, what are the inputs? The inputs are supposed to be the matrix, the coefficient matrix A, and the column vector B, correct? And what it should return? It should return the solution. Yeah, let me call it as SOLN. So that now clearly solution was not defined. It should tell you an error if you call the function now. I know we have both of them ready, but still actually it says some error. What's the error here? The SOLN is not defined. Obviously, it's not defined because we are trying to return something which is not even known to me first. So we have to actually tell it to something. Maybe if I just initiate it with an empty string, and that throws the error off, obviously, because it is having some value right now, no matter whether it's empty or not. So I want to return a solution. So how do I do that? What did we do? we first augmented the matrix. And then what did we do? We found the row echelon form of it. And then we looked the last column of it, correct? Yeah. I believe you can also do a dot column of -1. Let me check. Yes. Yeah. If you give a -1 on the column, then that actually starts from the last. So the -1 is the last column. Okay. If you look at that matrix A, then you will have idea. So the matrix A is, I'll show it here, I think, but what was my matrix A? The matrix A was 109, 11. This first column is 109, second column is -2 to 3, and the third column is 131, right? Now, if I write A dot column of -1, then what that's going to do? It's going to give me the last column of this A. Huh? Yeah, -2 will give you last but one. So it counts from the back. So then -3 will give you the last but 2, last but 3 actually. Last but 2, no? That's what you call that. So you can count it from the backward as well. Now, why is this helpful? Anyway, now I know that the order of the matrix is actually 3, so I can directly call it as 3. If you do not know, what I wanted was, I just have to pick up the last column. That I know, right? So the picking up a last column is simply A dot column of -1. So what we can do now is we can put everything together, and then in one single line, I'm going to do it. What I want to write now, I have to first augment B. And then what I should do, I should do a row reduced echelon form of it. And then I should take a column, the last column of it. You see, what did I do? I have actually chained the actions on top of each other. We call this as object-oriented programming. That on each object, we can call a method on top of that method. So RREF will be calculated on what has been actually given as an output. And then column of -1 will be actually got after the row reduced echelon form has been formulated. Such things are there. Yeah. So now it should work. And that's the answer. I'm just running that over here. So in fact, actually, what I can do is I can directly write this, take this fellow, and then return it like this. See? Yeah. So I delete the remaining things which are unnecessary. Now it's neater and sweeter so that we don't need to actually fiddle around what's happening here. Whatever has been done in last some 4 or 5 cells, I've done it in only one cell now. So that's the use of functions. So the function is actually going to combine some of the actions together which are related to some specific inputs to be done. Okay. Any questions so far? So let's do one thing. We'll practice a little bit more. We'll try doing Cramer's rule. I believe the spelling is correct. No. Can you tell me what's the Cramer's rule? If we have a system of equation AX equal to B, then I can solve the system using Cramer's rule if and only if the determinant of A is non-zero and the solution of such system is going to be equal to, anybody? The first variable solution will be equal to the determinant of the matrix A, in which that the first column is replaced by B divided by the determinant of A, right? Yes, sir. Yeah. So that's the Cramer rule. And similarly for the rest of the variables. So what we are going to do now, we're going to write a function which will do that job. Probably I will I will do that. But before that, what I wanted was I wanted some way that I have to replace the column with respect to what I have. For example, if A is there in my hand, then I should replace the first column by B. Then only I can solve the problem, right? Yes or no? Yeah. So how do I do that? So there is no special function for that in Sage Math. Like you can't directly replace the column. So for that, what will I do is that's a very good exercise. Let's write a function. We'll write a function called column replace. Now, what is that's going to do is it's going to take a matrix and it's going to take the column to replace, and it's going to take the vector, meaning in which column to replace, that's the column number, and what vector you want to replace on that particular column will be taken as a V. Okay. Specifically, I change this name so that should not confuse you with the A and B. Okay. Good. So how will I do it? Now, let's take N1 equal to this already, I think yesterday, N rows. Okay. Did we use it? I don't remember. So if I write M dot N rows of A, then that's going to give me number of rows of A. Maybe I'll show you here. You know, A is the 3 by 3 matrix. So if I write A dot N rows of, it's a method actually defined on a matrix class, and that returns the number of rows. Okay. Similarly, you have a number of columns as well. Okay. Fine. Now, what you can do is you can define M dot N rows of as my N1, and then you can also define N2 is equal to M dot N rows of. Okay. So what I usually do is I come over here and then keep verifying that whether this is okay or not all the time. Okay. So here is the A in my hand, meaning the A that I had in my hand. N dot columns. Yes. Thank you. I usually verify the function until a certain stage of every time. Otherwise, actually, we'll keep writing it a big function and then we'll lose track of actually the errors, and we'll end up correcting the errors. Debugging is a very difficult job to do it. Although there is a good amount of actually information is there in the error message still. So it's a good practice actually. Now you keep running the function and understand where is the error that you are committing it. Yeah. So I want to know whether I have committed any error on writing the first line. Okay. Fine. So how do I verify? It's simple. Just throw the inputs in. So what's the input? The input is actually A. The good way of actually giving is using keyword argument. Like what's the value of M? That's the A. And what's the column value that I want to replace? I want to replace let's say the first column. So the 0th index. And then the vector that I want to replace is B. Okay. So now if I run this, obviously it doesn't do anything, but it also doesn't throw any error. So that's a good sign. That means I call the function, still this does not throw any error, means there is no any error in this line. Okay. If there is a contextual error, that's a different story. There is no syntactical error. Obviously, it's not a problem. Okay. So then what am I supposed to do? Let me create a matrix with this number of columns and number of rows. And I'm going to fill that matrix with what I want, and then I'll return that matrix. Okay, that's the idea. So what I wanted to fill, I first wanted to actually take a copy of M and then store it as S. There is a easy way of doing it. It's just actually take a copy and then put it. But now I'll do a little rough way of doing it, that using for loop. Yeah. That is to just introduce the programming. But there's a better way of doing it, obviously. So what will I do? Now what I wanted, now what I did actually, let me return the S and then tell you what is it. Now you can see that if I actually have created a matrix with the specific order like this, then that actually gives me a zero matrix automatically. Yeah. So every entry now it is actually zero matrix. You know, M is actually 3 by 3. So it's going to be a 3 by 3 matrix where all the entries are actually becoming zero. So now what did I want? I wanted to replace all these entries by some other entries. So what are those entries? Well, actually what I wanted was every ij the entry of this one supposed to be the ijth entry of M. So how do I say that? Obviously, actually, I have no way of actually calling it right now. If I just simply run this, obviously it's going to give me an error. So first error is J is not defined. Yeah. Obviously, it is not defined. So how do I actually solve this problem? I should go along the rows, and for each row, I have to go along the columns and then pick up that row and then column element and then replace that with M of, replace that M of ij with S of ij. I'm sorry, replace that S of ij with M of ij. Meaning throw away all zeros, whatever is there, but fill those people with M of ij. So that's the idea. So for I in the range of N1 and for J in the range of N2. So now I am in for each row and for each column, I'm going to do this process. What is the process I'm going to do? I'm going to take the Mij and then I'm going to assign that Mij on S of ij. So that's the plan. So now if you look at it, it's whatever the matrix you are giving in, that should come out now, correct? Is it right? So I've created a S. Remember, initially it was giving me only 0, 0, 0, 0. Now, after I write these 3 lines of code, what was giving it? It is giving me whatever I was inputting. But now I have a control now. Now I know what to do as well. So what is that I have to do? After doing this, I have another way of actually controlling that. Actually, for that particular column, don't do anything. And after that, but I'm not right now bother about the efficiency of the code. So I'm not doing that. So what I have to do now? Tell me. Okay. I forgot to say that, I think. Suppose if I say actually range of 2 or range of 5, then that's the number between 0 and all the numbers between 0 and 1 with a step of size of 1. So the way you see that is it's a constructor. So if you run if you run a list on that range, then it will give you the numbers. So the range of 5 is nothing but 0, 1, 2, 3, 4. Okay. Now you can also start with some number, let's say actually 2 to 5. That's going to start with 2, 3, and 4. It's not going to end with 5. It's going to stop with before that 5. So the last index is never counted. You can also optionally give a step size as well. Maybe if I do a 10, all of these numbers. You can also optionally give a step size, let's say 2, for example. Then it's going to start with 2, and every time what's it's going to do? It's going to advance it by 2 units. So 2, and then next is 4, and then 6, and then 8. Obviously, the last number is 10. So it is reached. So it's not actually going to give me the 10. So obviously it is. So if I replace with 11, I should get 10 back. Yeah. So that's the range function. So the range function is giving you this flexibility of actually having the numbers. Okay, so now what we have done, let's complete this function. So what we have done right now here is we have created a matrix which was technically the same as that of M. Now what we want to do is we want to replace that column in which the values has to be changed. So how do I change it? Let's say I want to replace the 0th column. Okay, I'm assuming that actually I will give the correct column as it is using Python sense, not 1, 2, 3, but I'll say 0, 1, 2. Okay, that's the idea. So what I have to do? I have to do it on every row, right? On a particular column, I have to do it on every row. So how do I actually say for every row? So it's for I in the range of N1 what I wanted simply the S of I comma the corresponding column that I'm looking at. So the corresponding column, remember the column has been got as an input variable here. So that should be equal to M of I comma the corresponding column. Is that okay? Oh, I'm sorry. What I wanted the value from V, right? So V of I comma I believe actually V of I should work. Okay, let's see whether it works out. Okay, now it works. Yeah, what did I do? I picked up the first column and then replaced that column with. As I told you, there is a nicer way of doing it, very easy way of doing it without much of this kind of programming. Because I just actually picked up this way of doing it because in this way I can at least introduce for loop, function definitions, etc. The entire row can be actually completely replaced. That function is available anyway. I'll not introduce now. Okay. So now what we will do, let's say, first of all, let's write a function to have a Cramer rule, right? So solve using Cramer. So it should take A and it should take what? B. That's all, no? And it should return the solution. So what all you have to do? We have a function to replace all of them right now. Let me probably do one step outside, then later we'll throw the remaining steps in the inside the function. Or maybe I will leave it as an exercise. I think we already have a idea to do it. So I'll leave this as an exercise, but at least actually I'll do one step right now. So what is the first step that we want to do? I want to find X, correct? We have X, Y, Z variable, but the X is. So what's the X? The X is, that's a determinant of, how do we write that? I don't remember now. A, B, yeah. Let me write it like this. A, B, A, I'll write it like this, A1B, and I'll interpret it like the first column has been replaced by B. Is that okay? So the value of X is nothing but the determinant of A, in which the first column is actually replaced by B, divided by determinant of A. Okay. Similarly, the other things. I don't now remember actually how do they usually do it. I think there's a special notation to do that, but I think this is do the job right now. This will do the job. So how will I find now X now? So first thing actually I have to do a determinant, right? So how will you find the determinant of A in Sage Math? There is a function called det. Anything you think will be a function here. So that will give the determinant. And all that I have to do is, now I have to actually do it on A, where the first column is replaced by B. So how do I do that? Remember, I just have written a function to actually replace a column, right? So what can I do now? So I can use that function column replace, where it takes the matrix A, and what am I supposed to do? I should do the 0th column and replace it by B. So now I have a matrix in which the first column is actually replaced by B. Yeah. So let's call this matrix as A1B. I don't think so. I can name it by hyphen. A_1_B. Then what I need, I know X value is actually equal to determinant of A_1_B. That's the matrix in which the first column is actually replaced by B divided by determinant of A. Did we get the same solution? Yeah. Again, this exercise is not really mandatory unless you really wanted to do some programming inside. So that will give you a good exercise, good excuse of actually writing some program inside. So now what I do, you have to solve this problem. I actually leave it here as an exercise for you. So in the tutorial, what you can do, you can write a function which has been done like this. So now you can, first thing what you have to do is, one thing at least I will do without returning anything. If the determinant of A is suppose not equal to 0. So how do I say not equal? The way you say not equal in Python is this way. So an exclamation and then equal to. Yeah. And then you simply directly return that actually, meaning you stop the process because only the determinant is actually is not equal to 0, then only we can do it. Obviously, I should do the other way around. So if the determinant is equal to 0, then don't do anything. So how do I say don't do anything? Actually, simply I'll say that Cramer rule is not applicable. Like this. So there's an if statement. What is this? Actually, it does the small character check. If you are good, then only I will process the Cramer rule, otherwise I will not do it. So this return keyword is very important. Once you return it, anything else in the program, anything else in the function will not run at all. Okay. I may be having 1,000 lines after this return. If this return is actually has been supplied or thrown away, then nothing else below that will get run. So those things and all you have to write it as a function over here. So for example, what you can do now, you say if a dot n rows, now you can how to compare number of rectangular matrix now. If a dot n rows is actually equal to or not equal to a dot number of columns, then you say that actually is a must be square. That's all. Is that okay? So now if you supply a square matrix, let me probably will make a small square matrix for now. Sorry, rectangular matrix now. Okay, let's do a small single matrix. Obviously, it is rectangular, right? So if I say solve using Cramer of this A along with any B, it says clearly A must be square, right? Is it okay? I think that's a lot of programming. Let's move on. Okay. So yesterday, what we have seen that linear. We have seen vector spaces. We have seen how to find the basis for a vector space. We have seen how to look at the span of a particular set and then identify a particular element is actually inside the span, so on, so on, so on, right? Now, if you take any matrix you have, then that matrix has a 3 subspace attached to that. Can anyone tell me that? For every matrix has 3 3 subspaces attached to that. I'll write it colloquially, but you should understand what I'm saying. What are they? One is the column space of A, and the other one is clearly row space of A, null space. Okay. Now, Sage Math actually gives a pretty easy way of actually capturing them right away. So if I want a column space of A, then it's simply A dot column space of A. I mean A dot column space. That's all. Now, why it is simply a 1? That's because my A is different now. A is just single one-dimensional array. Can you notice? Let me give a good matrix at least. By the way, this small m, when you are writing it, it is trying to figure out what is the field and then trying to fit it. So if you have all integers, then it will consider that matrix as a matrix over ring integers. If you have a rational number, then the matrix over rational number, etc. So if you wanted to be controlling that, then one way of doing that is simply you pass a field over there, and therefore it will now consider that as a R, meaning real field. The other way of doing that is actually using the constructor using a capital matrix, meaning with capital M. So now if you look at it, and look at the type of A, now that will say that actually it's a generic dense matrix. That's all, right? If you change that to QQ, now it says generic rational dense. So if I would have simply left it as a small m, sorry, I think if I would have simply left it as a small m like this, then it says integer dense. So depending on whatever the number you have, actually it will try to identify the corresponding space. So if you want to have a control over, then either you do this way, where the field is specifically defined on that, and or using the other capital M. Pretty much the same job will be done. There's also two different way of looking at it. Like this RR is multi-precision floating point arithmetic. What that means is that you can actually, it will try to be very real as possible. Real precision, we call that as a real precision. That means it will go at 1,000 precision, 1,000 bits of precision, 2,000 bits of precision. It's possible, literally, realistically, it's possible. However, I also have two different spaces called RDF and CDF. Now, if you look at that matrix, you can see that this is real double dense. That means it's just a double number. Double number is nothing but it is just a real number with a double precision. Double precision is actually equal to 53 bits of precision. That means it's a fixed floating point arithmetic. That means RDF, it's a real dense field. Instead of RRR, if you use RDF, it's going to be first of all pretty much faster because it is going to work with a fixed floating point arithmetic. If you really don't bother about precisions, like 53 bits is already almost 17 decimal places. If you really bother about that, then you have to actually stick to RR. If you are not really bothering about actually now, okay, 17 decimal places is actually almost okay for me, then you should probably actually use RDF or CDF. Yeah, hopefully you understand that. Okay, CDF is the counterpart of it, that complex dense field. Okay, good. So now let's do the matrix over here. Okay, so let me, I don't know. Okay, let me do a 3 by 3 matrix for now. But actually you can have anything you want, right? So let me. Yeah, now you see that this is a column. The column space is actually, it's a vector space of dimension 3. Vector space of degree 3 and dimension 2. Degree is nothing but what's the dimension of each vector? That's the degree. That means it's actually is first of all a subspace of R3. That's what it says. So it's a subspace of R3 where the rank of the matrix A is actually 2. That's what this is. Clear, right? So the basis of the column space of A is actually given here. Okay. Now similarly, you can find out what is the row space of A. And that gives you another basis. Obviously, actually, the row space also should have the dimension 2. And that will have this basis. So this basis of the row space. So you can also find the null space of the A. I think it's called as kernel of A. Okay. You can also run rank on that. I think you can also run a dimension on that. For example, let's say I want to verify rank and nullity theorem. Can you tell me what is the rank and nullity theorem? What is the rank and nullity theorem? The dimension of V is actually going to be equal to dimension of the range of T plus dimension of the kernel of T, correct? Yeah. Or what did you say? I think nullity of T or whatever it is. Okay. Yeah. In matrices, what will you do? I mean, if you have a matrix, then what is the equivalent version of that? Yes. The number of columns of A, am I right? Yeah. Maybe I'll not do that. Yeah. So number of columns of A will be equal to rank of A plus nullity of A, correct? So this is the rank and nullity theorem for a matrix, because you know that the domain of A is the number of columns of A, meaning the dimension of the domain of A is number of columns of A. That means that works fine. So now all that I have to do is let's verify the rank and nullity theorem. That means A dot n rows, n columns. And what's that? That's, what did I write? I'm supposed to write n columns, not r columns. So number of columns is 3. Now I know that the column space will give you the rank by looking at the dimension. I can directly run the rank, but still, I just want to show one more function. So if you take any vector space you have, then you operate dot dimension on it, it's going to give you the dimension of that. Okay, fine. Then A dot kernel will give you, when kernel's dimension will give you the nullity. Yeah, I believe you can also run a nullity directly on that, and that also should return a 1. So if you want to have a nullity directly without finding kernel and then dimension later. You can also run a nullity on that. Yeah. So what I should do now, so I just have to check whether the number of columns of A, whether that's equal to A dot rank of A. I already told you I'm little being little bit on tour now, so just doing it a little bit longer. So A dot column space of A dot dimension will give you the rank of A, and then A dot kernel of A, meaning A dot kernel of will give you the kernel space or null space, and then running a dimension on that will give you the nullity of it. So yes, that's good. Is it okay? You can also find the left kernel. The left kernel is usually you solve this equation, right? If you solve this equation, instead of solving ax equal to 0, if you solve xa equal to 0, keeping x's in the row. So whenever I write like this, actually, I believe you understand the appropriate order. Obviously, x, if you keep it on column, that doesn't make any sense. You have to keep it on row. Otherwise, I should write x transpose. I believe actually you understand those small constraints. We call this x as our set of all solution of this system as a left kernel of A. Yeah. So that is also a subspace. And that is also one of so-called 4 fundamental subspaces. So 4 fundamental subspaces are of a matrix A. 4 fundamental subspace of A. What this is pathetic spelling I have written. So 4 fundamental subspace of A. One is the column space, and then the other one is the row space. The other one is the null space. We also call this as right kernel of A. The last one is the left kernel of A. I don't know whether they have any name for left kernel, like null space. So given any matrix A, we can find all these 4 subspaces. There's a lot of things actually, people play with that. Okay. Right. Now, given any vector space like this, you can also find a basis, correct? How do you do that? Let's say we have a column space, that's the vector space we have. And then if I run a basis on top of it, that gives me the basis back. Yeah. I don't know, maybe I would have forgotten to tell this in the previous class. Okay. Any doubts so far? 0? Yeah, but that you cannot catch, no? For example, A dot column space, if you call it, and then let's say, suppose column space like this, and then the column space will give you everything what you need. But if I do this instead of this, which gives me only the basis. So if you need the basis exclusively, then you have to do it, right? Because this one doesn't make any sense, no? Like so many letters, words, everything. Yeah. The way you extract the basis is, I think this is the best way of doing it. Just for a look, yes, that the column space itself is fine. That's how actually it's been, the print function has been written actually. Okay. So you all know Gram-Smith process. What is the Gram-Smith process? It will take a set of vectors and it will convert into an orthonormal basis out of it. Right? It will construct an orthonormal basis out of it. If there are dependent vectors, it throws away. In fact, it leaves you zero, but you can throw it away later. That's the plan Gram-Smith process does, right? So I'll give you a small exercise. Write a function to to perform a Gram-Smith process. You know how to formulate the each and every orthogonal vector. So why don't you write a function to have a Gram-Smith process? Gram-Smith obviously actually the sage math has its built-in version of calculating it, but I think probably it's a good exercise for your programming skills. So next with A, let's say you have any A, then what is the maximum you would like to try with the A? Not maximum. What is the other thing that you will try to do with the A is using, trying to find the eigenvalues, eigenvectors, etc. So they're all already built in Sage Math. If you look at it, A dot eigenvalues of, then it will give you the eigenvalues. You see A dot eigen vectors. Yeah. Here also, there are two different eigenvectors you can define. One is left eigenvector and the other one is right eigenvector. We usually look at the right eigenvector, right? All our applications are actually in the right eigenvector. Therefore, A dot eigenvectors underscore right will give you the eigenvalue and then corresponding eigenvectors. Okay. So the first one is now eigenvalue and then corresponding eigenvector. I don't know whether the show method will work on this or not. Let me check. That works, but it's pretty nasty. It gives me only one eigenvector, so it's not good. Yeah. You can ask for eigenmatrix. Then it shows the proper vector. Okay. The eigenvector, eigenmatrix, right? Ah. Each column is an eigenvector. Okay. So then probably I can call now, like I'll call it as EA now. I know that EA of 0. By the way, this way of calling is actually calling a person by its index, like roll number 1, roll number 2, roll number 3. It's just calling them. You have two people in the array. That means the first person is always called as 0. Second person is actually called as 1, 2, 3, etc. Okay, fine. So this is the eigenvalues, and we have the corresponding one eigenvector. Where is the one? Okay. This is the algebraic multiplicity. Algebraic multiplicity of this this eigenvalue. Yeah. So you can see that the eigenvectors right also gives you a third argument over here, 1, and that's the algebraic multiplicity of this one. That the corresponding eigenvector, the eigenvalue. You know that the A we have taken, we were using it from the starting. That's invertible, so obviously all the no, yeah, it's invertible. That's all. Just the column space is actually already 3 dimension, and all the eigenvalues are actually distinct for all the algebraic multiplicities are 1 automatically. Okay. So you can see this one, I see the other one actually was giving it in the kind of row vector, but now you see this is the eigenvalue and the corresponding eigenvector is listed in the first column. Yeah, 0.64, 0.64, 0.41, etc. Hmm? A is not singular. No, A is not singular. We have used grammar rule, remember? Let me show. Okay. I understand what's the problem. Yes. Actually, yeah, your observation is correct. What is happening here is actually one of the eigenvalue definitely must be 0. You know that it's a singular matrix. So rank is 2. And it's not showing as a singular, it's 0. But you can see that actually it is over here. You see the last eigenvalue is minus 3.64 into 10 to the power minus 17, which is almost close to 0. So this happens if you do a calculation in the multi-precision arithmetic. So it's trying to make it as close as possible. That's the problem. Yeah. So probably if you do it on CDF, this will not be a problem. Let me check whether probably anyone have any idea actually how do I in the middle itself I can change that. So one way of doing it is very crooked way of doing it is I think A equal to matrix of CDF or RDF. Let me check whether it will work or not. Yes. Yeah, now also it gives me that much. I don't know. This is one problem is there. That numerical approximation will actually tell you to consider this as a non-zero, but that's not actually non-zero. That should be supposed to be 0. This problem is always there. Or maybe QQ will give you a real. Yeah, that's good. If all your values are this only integers or rational numbers, then you can use this. But again, there's always a problem like that. Even we feel that actually, no, why is it happening? It's not properly implemented. Yeah. Always this numerical error is a problem. You know. So, these kind of problems obviously occurs in many times. So we have iterative methods for approximating that eigenvalues, you know that, right? Eigenvalues and eigenvectors, obviously. Now, the one of the best way of finding largest eigenvalue in the matrix is using power method. And what's power method? What do we do usually? We start with some x naught, and then we'll find out whether that is actually equal to some lambda times x naught or not. Obviously, that's not going to be equal. Therefore, what will you do? You'll keep finding it until you have this kind of relationship. Yes. So what will you do now? You will try finding the maximum element in the, so let's say you have a x1 here. That's the way we have got it. Now you take the maximum of x1 and then bring it outside. Then whatever the remaining thing actually is there, that you use it as x naught now. Then you multiply that and try finding that whether that is now is an eigenvector or not, etc., etc. Okay. So that's the power method, correct? Let's probably write the code in another 2 minutes so that our tea will come. He has actually come. So let's write a function probably. I'll write partially, I'll write the function, then remaining I think you will fill it up. Okay. So power method. The power method has to take the matrix A as an input. And in any iteration method, what we have to look at something called as a tolerance then only we can actually avoid the infinite loop problem. Like you keep looping it, and then you will never actually end up with a solution, because obviously the iteration methods has been obtained because of the numerical approximation errors. So you have to somehow actually sacrifice something, right? Question in the chat. Yes. What is the question? There are many questions out there. So what if round off to some place? Yeah, we have what if we round off to some place value? Like if I understand the question properly, I think what she was trying to ask is, what if can we not round off to some other decimal places? Yes, that's possible. Yeah. If I what's the function? Vinay, do you remember? I believe actually there is a numerical approximation. Yes, there's a function called the numerical approximation. Yeah. And you can give any number you want. Maybe something like this. And then you can give the precision in bits, maybe 53 bits or whatever it is. So that will give you the numerical approximation until that. So 53 bits is usually close to 16 to 17 decimal places, approximately 17 or 25 decimal. 16, 16 decimal places. Okay, that's it. Now you can also have some 100 bits like this. So this way, actually, what you can do, you can actually numerically approximate those numbers with respect to that bits of positions. So in Sage Math, actually, they round it off with respect to the bits. You have a way of doing it. So you can have pretty long precision like this. Is 1000 bits of precision. So 45 by 23, if you look at that decimal expansion, then it is rounding off to 1000 bits of precision. I don't exactly know what is the number of decimals. I think 1000 bits means, let's assume that actually 53 bits is 70 decimal. So let's calculate it. Okay, I should do. Yeah, it's like 320 decimal places, approximately. Some 300 decimal places. Yeah, okay. Very powerful if you use Sage Math, because right now, even when we had one work with, when we had one work on the iterative methods, me and Vinay had discussing that the other Python programming, all of them are actually working with double precisions. That means the maximum decimal places will get to some 16, 17 decimal places. But for our iteration methods, to verify the validity and then the quality of the iteration method, everything, we needed a longer decimal places approximations. So that time, what we did actually, we had to come back to Sage Math only for that. So all our codes are now in Sage Math for that particular paper. Okay. Anyway, so that's fine. Okay. Probably I think we'll have a break, and after that we'll write the function for power method and do some more decompositions and other stuff. Okay. Yeah. Shall we break for some time? So we'll have a break for how long? 10 minutes. Is it like, this means what? This means, is it 10 minutes or? $15 minutes break. Yeah. So we'll have 15 minutes break. So it's already 11 now. So we'll start by 11:15.